Hello, this is Gregory Maxwell, and this lesson is about graphs of equations. In this lesson, we'll be talking about symmetry and increasing and decreasing graphs and so on. I'd like to give a PowerPoint credit to Professor Shauna Hader from Salt Lake Community College, on which many of the slides of this PowerPoint are based on her PowerPoint presentation that she created. So let's start off by talking about symmetry. In this course, we'll be talking about three types of symmetry. And when we talk about symmetry in a graph, we are talking about when matching points relate to another point. So you choose a point and there's a matching point for that follows a particular system. So symmetry in a graph is when there's matching points on both sides of a dividing line or around a certain point. And the matching points are called the image about the point of the line. So one type of symmetry is y-axis symmetry, in that the points on one side of the y-axis match up with the points on the other side of the x-axis. So they have a mirror effect. Another type is x-axis symmetry, which works the same way, except that the mirror line is now the x-axis. And then there is origin symmetry. And in origin symmetry, it's symmetry about the origin. Basically, you're rotating 180 degrees to get a matching point. Now, let's talk about that a bit. And while I'm going through this, what I will do is I will save some slides as we go along. So let's talk about the symmetry. Let's first talk about x-axis symmetry. For x-axis symmetry, for a given point, let's use the point 6, 4 as an example. For a given point, there is a corresponding point across the x-axis as if it's a mirror. So if you treat the x-axis like a mirror, on the other side of the x-axis there's a matching point that matches with the point 6, 4, which means the x-coordinate will stay the same, but the y-coordinate will change to the opposite. So the negative of the y-coordinate. So the point 6, 4 matches with the point 6, negative 4, and that is what happens when you have x-axis symmetry. To get a point symmetric with respect to the x-axis, think of the mirror image of or flipping it across the x-axis. So for each point xy, there's a corresponding point x, negative y when we have x-axis symmetry. Now let's see what happens when we have a graph. When we have a graph, what we do is we start off with a line segment or a piece of a graph, say this graph here, and then we're going to reflect every point correspondingly across the y-axis. So we have a graph that looks like this. As you can see, each point has a matching point across the x-axis. So there we're flipping it. And basically what we're saying is for every point on the graph, xy, we have a corresponding point x, negative y on the same graph. As you can see, if you have x-axis symmetry, this graph is not a function because it fails the vertical line test. Now that we've done x-axis symmetry, the basic idea of x-axis symmetry, let's talk a little bit about y-axis symmetry. In y-axis symmetry, you also have a point. Let's start with the point 6, 4, but now the mirror is the y-axis. So a corresponding point will have the same y-coordinate, namely 4, but the x-coordinate will be the opposite, negative 6. So the matching point, the mirror image, the image point is negative 6, 4. In other words, what we have done here is we have matched the point xy with a point x, negative y. So to get a point that is symmetric about the y-axis, what we do is we change the x-coordinate. And as you can see there's a little pattern. If we want to reflect about one axis, we simply change the coordinate of the other variable. So to get symmetry about the y-axis, change the x-coordinate, and to get symmetry about the x-axis, change the y-coordinate. Now, let's do it with a graph. Same graph here. Now, since we're doing y-axis symmetry, then the graph will go in the opposite direction. So as you can see here, this does not fail the function condition. So you can have graphs that have y-axis symmetry that are also functions. You may have graphs that have y-axis symmetry that are not functions, but the fact that a graph has y-axis symmetry doesn't mean it won't be a function. In fact, in another lesson, we'll talk about a special type of function that has y-axis symmetry, and that type of function is called an even function. So with y-axis symmetry, we replace all the points xy have a corresponding point negative xy on the same graph. Let's talk about origin symmetry. With origin symmetry, we're doing two reflections basically. We're reflecting about the x-axis and about the y-axis. So point 6,4 is also going to have a corresponding point. In this case, it's kind of like turning the graph on its head. You're going to flip it about the y-axis and also about the x-axis. So the x-coordinate will change and the y-coordinate will change. So the new point will be -6, -4. Because now we're not simply talking about reflecting about one axis, we're reflecting about both axes. So we have to change both x-coordinate and y-coordinate. And of course, when we do the graph, as you can see here, the graph is now going to be, the point is going to be reflected about the x and y axis together, which effectively is like rotating the graph 180 degrees. So what we have here is a nice little situation where in order to get our origin symmetry, you just change the x and the y coordinates. Change the signs of the x and the y coordinates. Now, as you can see, this could also be a function. And in fact, whenever you have a function that has origin symmetry, we call that an odd function. And we'll talk about that in another lesson. So let us summarize what we just went through here. If we're given an equation, you can test whether the graph of the equation has symmetry by doing the following. If you want to find x-axis symmetry, just replace all your y's with -y. Simplify, and if you get the same equation that you started out with, then that graph has x-axis symmetry. If you want to find y-axis symmetry, replace all the x's with -x. Simplify the equation. If you get the same equation as you started out with, then we have x-axis symmetry. For origin symmetry, you interchange both. You replace x's with -x's and y's with -y, and you simplify and check to see if the equation is exactly the same as before. If that's the case, then you have origin symmetry. Of course, there may be cases where you have x-axis symmetry but not y-axis symmetry, or y-axis symmetry but not x-axis symmetry, or origin symmetry but not either of these. Or you could have a case where the graph doesn't have any of these symmetries at all. That's totally possible. So let's do an example here. Here's a graph, an equation of a graph. We have y squared minus x minus 4. We want to test to see if this graph has x-axis symmetry, y-axis symmetry, or origin symmetry. To test for x-axis symmetry, what we're going to do is take all our y's and replace them with -y. All right? Now, once we replace that y with -y, we simplify. Now, -y squared is the same as y squared. So when I simplified, I ended up with the same equation as I started out with. Because I ended up with the same equation that I started out with, then we know that this graph has x-axis symmetry. And that is because when I replaced all the y's with -y and simplified it, the original equation is what I get. Now let's test to see if the same equation has y-axis symmetry. Now I will replace all the x's with -x, and then I simplify. Now, because I have minus and negative, that's going to give me plus. So y squared plus x minus 4. As you can see, this equation is not the same as the original equation. The original equation had a minus x and the new equation had a plus x. So there's no way to turn one equation into the other one without fundamentally changing the equation. So the two equations are not the same. Therefore, this equation, the graph of this equation, does not have y-axis symmetry. Now let's check for origin symmetry. For origin symmetry, we replace all the y's with negative y and all the x's with negative x. Then we simplify. So the y's get replaced with negative y and the x's get replaced with negative x. And as you can see, this equation is not the same as the original equation. So we do not have origin symmetry here either. So this example we just did, the graph does not have y-axis symmetry. It does have x-axis symmetry, but it does not have origin symmetry. It only has x-axis symmetry. Now, we're going to do a few examples in a few minutes, but let's just point out a few things before we get to some examples here. So, a few more things before we get to example. Graphs also have what we call x and y intercepts. An x-intercept or a y-intercept, an intercept is just where the graph crosses that particular axis. So, for example, for x-intercepts, we're looking for the points where the graph crosses the x-axis, in which case the y-coordinate will be 0. So the x-intercept here is 6, 0. The x-intercept here is -1, 0. The x-intercept here is 2, 0. As you notice, every x-intercept, the y-coordinate is always 0. And so it's very easy then to find x-intercepts. Well, relatively easy. To find x-intercepts, you simply replace all your y's with 0. You substitute 0 for y and then solve for the corresponding x value or values. Similarly, to find y-intercept, you're looking for places where the x-coordinate is 0. And that's where the graph crosses the y-axis. So in this case, the x-coordinate for the straight line, the y-intercept for this straight line is 0, 4. For this curve, it's 0, 2. For this curve, it's 0, 5. Again, what we know is that all the x-coordinates are 0. And so we have y-intercept. We're looking for y-intercepts. We substitute 0 for the x-coordinates and then solve for the corresponding y-coordinates. All right, now let's do a quick example here. Let's say we want to find the x-intercept for this graph. So I want to find the x-intercept for this graph. I simply take the equation and replace all my y's with 0 and then solve for x. And I will only get one x value here. That x-coordinate is x equal to 6. So when y is equal to 0, x is equal to 6. So that's 1 point on the graph. Now, let's go on and continue here. And this time we're going to find the y-intercepts. To find the y-intercept, I replace all the x's with 0 and solve for y. In this case, I get y is equal to -4. So now when I replace all the x's with negative x, when I replace all the x's with 0, the y-coordinate is -4. Since this is a straight line, we can just draw a straight line through the 2 points. And that's the graph. It's relatively easy to draw the equation of a line. As we've seen in previous lessons, you just need 2 points to draw the graph of a line. So when you're graphing a point, an equation is usually helpful to isolate one variable, preferably y, because usually functions have y isolated, but it's not absolutely necessary to be y. It's just y is preferred. Find x and y intercepts, make a table of points and plot those points, and then try to draw a smooth curve, or if it's a straight line, draw a straight line to go through the points. Now, let's try a few quick examples here. So in this question, it says, for each equation, list the intercepts and test for symmetry. So let's start off with this one. Let's look for the intercept. For my y-intercept, I will simply replace all my x's with 0 and solve for y. And so in this case, y is equal to positive or negative 2. So my y-intercepts would be the points 0, negative 2 and 0, positive 2. There are two y-intercepts on this graph. So of course we know this graph is not a function, because a function cannot have two different y-coordinates that correspond to the same x-coordinate. Now for x-intercepts, I just replace all my y's with 0 and solve for x. And that gives me x is equal to negative 4. So my point here is negative 4, 0. We put the x-axis, the x-intercept first. Now, let's try. Let's check for symmetry. To check for x-axis symmetry, I simply replace all my y's with negative y. And then I simplify the equation. And when I square negative y, I get the same as when I square positive y. And so as you can see here, this graph has x-axis symmetry. Then to check for y-axis symmetry, I replace all my x's with all my x's with negative x. So we'll get y squared is equal to negative x plus 4. Clearly, it is not the same as the original. So this does not have y-axis symmetry. And then for origin symmetry, I try both ways. I replace all my y's with negative y and all my x's with negative x, and I simplify. And as I can see that I do not get the same equation as above, so we do not have y-axis symmetry. So we don't have origin symmetry. We only have x-axis symmetry. Only x-axis symmetry. Now, I'm going to invite you to try number 56 on your own, and it is very similar to what we just did. So I won't go through that one since I just did number 55, but 56 is extremely similar to what we just did. So let's move on to question number 57. For question number 57, we want to find intercept. So to find the y-intercept, I will replace the x with 0. So I do the cube root of 0, which is 0. And to find the x-intercept, I replace the y with 0. So we have the cube root of x is equal to 0. Of course, that implies that x is equal to 0. So there's only one intercept because it's the same intercept for both. The intercept is 0, 0. Now let's check for symmetry. For this to have x-axis symmetry, we need to replace all our y's with negative y's. So I have negative y equal to the cube root of x. If I try to get the y by itself, I end up with the negative cube root of x. Clearly not the same. So this does not have x-axis symmetry. Let's try to see if it has y-axis symmetry. So I do, for y-axis symmetry, I'm going to replace my x's with negative x. So now I have y is equal to the cube root of negative x, which is if we simplify that, it's just y equal to negative the cube root of x, because cube root of a negative is the negative of the cube root of the positive. This also does not have y-axis symmetry. Now let's try for origin symmetry. Origin symmetry. Let's check to see if we can get that one. So I'm going to replace my y's with negative y, and I'm going to replace my x's with negative x. And as you can see here, that means negative y is equal to the negative of cube root of x. And then if I divide both sides by -1, I get y equal to cube root of x, which is my original expression. Therefore, we have origin symmetry only. Origin symmetry only. And again, I would recommend that you try number 58 on your own. It's a very, very similar question. Let's try a few more questions here. And as you can see, these are from the indicated textbook, Algebra and Trigonometry, 9th edition by Sullivan. And we're going to do a few of these questions here. Now, we did one similar to this question here, x squared plus y minus 9 equal to 0. In the review of the notes. So we're just gonna rehash that question again. So let's see. First of all, let's find out our intercepts. So for my y-intercept, I'm going to replace my x's with 0. 0 squared plus y minus 9 is equal to 0, which implies that y is equal to 9. And then for my x-intercept, I'm going to replace my y with 0. So I have x squared plus 0 minus 9 equal to 0, which would mean x squared equals to 9. So that means x is either equal to positive or negative 3. So my intercepts here are the points 0, 9, that's my y-intercept, and then we have negative 3, 0, that's one x-intercept, and 3, 0 for the other x-intercept. Now, let's talk a little bit about the symmetry. Let's see if there's any x-axis symmetry. And to find the x-axis symmetry again, we're going to replace our y's, with negative y. So I'm going to have a plus negative y here. And when I try to simplify this, I realize that it is not the same as the original equation. So this graph does not have x-axis symmetry. Let's see if it has y-axis symmetry. For it to have y-axis symmetry, we simply replace all my x's with negative x and simplify. So we end up with x squared plus y minus 9 equal to 0. And that definitely has y-axis symmetry. Now let's check finally for origin symmetry. For origin symmetry. And if this equation, if this graph has origin symmetry, then what we would need to do to verify that is replace all the x's with negative x and all the y's with negative y, and see if we get the same equation as we did before. The negative x squared is just x squared, and when you subtract, you add a negative y, it's like subtracting y. That is not the same as the original equation, so we only have y-axis symmetry. Only y-axis symmetry. Now let's try another one here. Let's go with this number 61. I leave you to do number 60 on your own. Number 61. What we do here is we check for your intercepts. And in fact, well, I would like you to try number 62 when we're complete. We are to check for our y-intercepts. We simply replace all our x's with 0. And that would mean y squared is equal to 9, which means y is equal to positive or negative 3. And then for x-intercepts, we replace all the y's with 0. And then that means x squared is equal to 4, which means x is equal to positive or negative 2. So my intercepts, I have 4 of them in all. I have 2 y-intercepts, namely 0, negative 3 and 0, 3. And my x-intercepts are negative 2, 0 and 2, 0. Those are my intercepts. Now, let's talk about symmetry. X-axis symmetry. As before, we will replace all our y's with negative y. 9x squared plus 4 times negative y squared is equal to 36. So then I simplify, I get 9x squared plus 4y squared equals to 36. Turns out this one checks out. Then for y-axis symmetry, I will simply replace all my x's, with negative x. So I have 9 times the square of negative x plus 4y squared is equal to 36. I simplify that, and what do you know? 9x squared plus 4y squared is equal to 36. Same as the original equation. So that also has y-axis symmetry. And now for origin symmetry, we're going to replace all our x's with negative x and all our y's with negative y. And then we will see what we get. Turns out both of them work out to be exactly the same as they were before. And therefore, this graph also has origin symmetry. So therefore, this graph has y-axis symmetry, x-axis symmetry, and origin symmetry. All right. So they are actually graphs with all 3 types of symmetry. So now I would recommend that you try this question, number 62, on your own, and then we'll move on to another example. Let's try another example here. Let's say we try these questions right here. So for number 65, and now at this point I'd like you to try these before you can pause the video, and you can try these questions ahead of time and see if you get them correct. And if you do, then that indicates you're on the right track. If you don't, then you'll know what you need to focus in on to see where your point of misunderstanding or unclarity is. So for the intercepts here, for the y-intercept, we do y equal to 0 squared minus 3 times 0 minus 4, which is equal to negative 4. And for the x-intercept, we say 0 is equal to x squared minus 3x minus 4, which that's a quadratic equation, which we can solve by quadratic formula or by factoring. I'll do factoring here. So we have x minus 4x plus 1. And then that will mean that x is either equal to negative 1 or x is equal to 4. So my intercepts are 0, negative 4. That's my y-intercept. And my x-intercepts are 1, 0, and 4, 0. Now let's check for some symmetry. So for x-axis symmetry, we simply replace all our y's with negative y. So we have negative y is equal to x squared minus 3x minus 4. If I try to get the y to be positive, I get negative x squared plus 3x plus 4 on the right-hand side of the equation, which is not the same as the original. So that does not have x-axis symmetry. Let's now try for y-axis symmetry. For y-axis symmetry. So we have y is equal to replace all the x's with negative x and see what we get. If we get the same as the original, then we have ourselves a y-axis symmetry. If we don't get the same as the original, then it does not have y-axis symmetry. And as you can see here, the original is y equal x squared minus 3x plus minus 4. We have y equal x squared plus 3x minus 4, not the same as the original. So there we do not have y-axis symmetry. Now let's try for origin symmetry. And in this case, we're going to replace both the x's and the y's with their negatives. So we have negative y equal to negative x squared minus 3 times negative x minus 4. Now let's see what that gives us. We still have the negative y, and we have x squared plus 3x minus 4. And then if we try to get the y squared by itself, we realize here that y squared, when we try to get the y by itself, we still do not get the same as the original. We simply get negative x squared minus 3x plus 4. So that means we are not dealing with any of the standard symmetries. No symmetry, at least none of the symmetry that we're dealing with here. All right. Now, again, I'd like you to try number 66 on your own before I proceed with it. But so you can pause the video and then continue on to see if you can do the questions on your own first and then pick up afterwards. So let's take a look here. For the y-intercept, we have y equal to 0 squared by plus 4, which is just 4. For the x-intercept, we get 0 equal to x squared plus 4, which would imply that x squared is equal to a negative 4, which doesn't happen. There's no real number that works that way. So since there are no real numbers that give you a negative when squared, there is no x-intercept. So no x-intercept. So the only intercept we have then is the y-intercept, which is 0, 4. Now let's check for some symmetry. For x-axis symmetry, we're going to replace all our y's with negative y. So we have negative y is equal to x squared plus 4. If I multiply both sides by negative y, by negative 1, I get negative x squared minus 4. Y equal to negative x squared minus 4. This is not the same as the original. That does not have x-axis symmetry. Let's try for y-axis symmetry. For y-axis symmetry, we replaced all the x's with negative x. So now we have y equal to negative x squared plus 4. And if you simplify that, you get y equal to x squared plus 4, which is the same as the original. So yes, that works. And now let's check for origin symmetry. For origin symmetry, we replace both the x's and the y's with their negatives. And that gives us negative y is equal to x squared plus 4, which is not the same as what we had before, even when we tried to get the y by itself. So this one does not have origin symmetry. So this graph only has y-axis symmetry. Let's continue with this more little complicated looking question here. Let's try to find our y-intercept first. To find our y-intercept, we simply replace all the x's with 0. So we end up with negative 0 cubed over 0 squared minus 9, which is 0 over negative 9, which is 0. And if I replace my y's with 0 for the x-intercept, I get 0 is equal to negative x cubed over x squared minus 9. The only way a fraction can ever give you 0 is if the numerator is equal to 0. And so this will give you the same x equal to 0. So the only time we have an intercept here is at 0, 0. Now let's check for some symmetry, x-axis symmetry. To check for x-axis symmetry, I replace all my y's with negative y, and I try to simplify to see if I get the original equation. So negative y is equal to negative x cubed over x squared minus 9. If I multiply both sides by negative 1, that will give me y equal to positive x cubed over x squared minus 9. Please note that I did not multiply the numerator and denominator both by negative, only one of them, in which case I chose the numerator. Multiply the numerator only by negative 1, and we get an equation that is not the same as the original. So there is no x-axis symmetry. For y-axis symmetry, I will replace all the x's with negative x. So we now have y equal to negative of negative x cubed over the square of negative x minus 9. Simplifying that, we see that negative x cubed is the negative of negative x cubed, which is just positive x cubed. And then the denominator will work out to be x squared minus 9. This is not the same as the original either. So this graph does not have y-axis symmetry either. Now let's check to see if it has origin symmetry. So for the origin symmetry, we replace the y with negative y, and replace the x with negative x, and we simplify. What we end up with is negative y is equal to positive x cubed over x squared minus 9, which then will give us y is equal to negative x cubed over x squared minus 9, which is the same as the original expression. So this graph has origin symmetry only. The only one of the three. All right, now this last example is very similar to what we just did with a little caveat here. So let's just do it. I'll start it off and you can finish it. Y-intercept. To get a y-intercept, we have to set x equal to 0. Problem is, if I set x equal to 0, I'll be dividing by 0 here. And that does not give us solutions. So since there's no solution to that, this is undefined. In other words, there's no such number that works. Since it's undefined, then there's no y-intercept. No y-intercept. And then we can try for the x-intercept. For the x-intercept. To try for the x-intercept, we replace 0 for the y and solve for x. Now again, as I said before, if you have a fraction that's equal to 0, it's only because of the numerator. And if x to the 4 plus 1 is equal to 0, that would mean x to the 4 is equal to negative 1, which gives no real number solution. So there's also no x-intercept. No x-intercept. So this graph has no x or y intercepts. I'm going to leave it to you to figure out whether it has x-axis symmetry, y-axis symmetry, origin symmetry, or none of the above. For the next portion of our little exploration of functions here, of graphs and functions here, we're now going to talk about special types of functions, namely odd and even functions. An even function has y-axis symmetry. It is a function that has y-axis symmetry. And an odd function is a function that has origin symmetry. So an even function is a function that has y-axis symmetry. And an odd function is a function that has origin symmetry. Let's recall what we just said here. If we have a graph that's even about the x-axis and about the y-axis on either side of the y-axis, that means for every point xy, there's a corresponding point negative xy, then that graph has y-axis symmetry. We call that function an even function. So an even function is one where if you replace all the x's with negative x, you will get the same y value. An odd function is symmetric about the origin. So when you talk about an odd function, what you do is if you replace all your x's with negative x, then the corresponding y will also change signs. So each point xy has a corresponding point negative x and negative y on the same graph. So that's a graph with origin symmetry. And so a function that has origin symmetry, if you replace all your x's with a negative x, then your y values will change as well. And let's see here. For x-axis symmetry, as I pointed out before, if a graph has x-axis symmetry, then it is not a function because the graph fails the vertical line test. In fact, the only function that has x-axis symmetry is the line y equal to 0, which is the x-axis. So how do we tell if a graph is even or odd? Or do we tell if a function is even or odd? Well, the way we tell that is by using the simple test. If it's an even function, when you replace the x's with negative x, you should get the same result. In other words, f of negative x is equal to f of x for whatever x value you use in the domain. So, to check if this function, for example, f of x equal to 5x to the 4 minus 2x squared plus 1, is it an even function, I will replace all the x's with negative x. In other words, I will find f of negative x. When I do that, I realize that I get exactly the same equation as I had before. So this function is an even function. The graph has y-axis symmetry. Let's try this other function, f of x equal to 2x cubed minus x. I find f of negative x by replacing all the x's with negative x. And I do not get the same as the original. So that is not an even function. So when I replace x with negative x, in other words, when I find f of negative x, if I get the original equation, the original expression for the function, then that is an even function. But if I do not get the same, it's not an even function. For another function, if I replace all the x's with negative x, then the output is also going to be change sign. So f of negative x will equal to negative f of x. So I just need to figure out if I get the opposite of the original. So to check this one here, the same original function that when we replace x with negative x, we got the same as the original. It's not the opposite. It's not the negative of the original. It's the same as the original. So it's not an odd function. For our second example, when I had found f of negative x, I ended up with negative 2x cubed plus x, which is this opposite of the original. In fact, if I may indicate here a little bit, I could factor out a negative 1 from the resulting expression, and what is remaining inside the parentheses is the original expression. So this is the negative of f of x. So that's how we know that we're dealing with an odd function. When I replace x with negative x, we end up with the negative of the original equation, the original function. Now, there's a nice little rule to help us to remember what's going on here. All right? So we're going to get to that in a minute. Just a side note here, I forgot to do this quick example. If a function is neither odd nor even, if it's not odd nor even, we just say it's neither. Just as a number may either be a positive number or a negative number, or neither. That number would be 0. That's neither positive nor negative. So if I replace the x with negative x, I do not get the original equation, and I also do not get the opposite of the original equation. So it's neither odd nor even. With this expression here, when I replace x with negative x, I do get the original equation, so that is an even function. As a quick little side note here, if you have a polynomial with all the degrees, all the exponents of x being even numbers, then it's an even polynomial, and 2 is 2x to the 0. If you have a polynomial with all the degrees, all the exponents of the variable being odd numbers, and there's no constant by itself, then it's an odd function. But if there's a mixture, it's neither. And let me just show you again that if I factor negative 1, I do not get the original. They're not the same. So this is not negative f of x. And this is not f of x. So it's neither odd nor even. Here's another little nifty trick. Odd functions, are analogous to negative numbers. That means they kind of operate like negative numbers, and even functions are analogous to positive numbers. So they kind of operate like positive numbers. So remember, with positive and negative numbers, if you multiply two numbers with the same sign, or if you divide two numbers with the same sign, you'll get a positive result. A positive multiplied by a positive is a positive, and a negative multiplied by a negative is a positive. Likewise with division. If you divide a positive by a positive, you get a positive. If you divide a negative by a negative, you get a positive. And if you multiply or divide mismatched, that means they have different parity. One is odd, one is even. Sorry, one is positive, one is negative. If you multiply a positive by a negative, you will get a negative result. If you multiply a positive number by a negative number, you get a negative result. Likewise with division. The similar thing happens with functions. If you multiply an even function by an even function, the result will be an even function. And an odd function multiplied by an odd function will also be an even function. But if you multiply an even function by an odd function, the result will be an odd function. Same thing applies to division. Even functions work like positive numbers. Odd functions work like negative numbers. When you add two numbers with the same sign, you get that sign. A positive plus a positive is a positive. A negative plus a negative is a negative. Likewise, if you add an even function to an even function, you'll get an even function. And if you add an odd function to an odd function, you'll get an odd function. But if you add a positive number to a negative number, the result is inconclusive. The answer could be either positive, negative, or zero. So likewise, if you add an even function with an odd function, then you should get neither result. Neither will be the case because there are more than one possible outcomes for any given number that you plug in. So that's a little way to remember some of the rules. Okay, let's do a quick little exercise here. These questions are taken from the Algebra and Trigonometry by Sullivan, section 3.3. Let's take a quick look at this. All we're going to do here is determine whether from the graph whether the function is odd, even, or neither. As you can see, this function is clearly symmetric about the y-axis. It has y-axis symmetry, so that is an even function. Likewise, this function has y-axis symmetry, so that's also an even function. This function does not have y-axis symmetry, so it's not an even function. It does not have origin symmetry either, so it's not an odd function. It's neither odd nor even. Likewise, this function here has neither origin nor y-axis symmetry, so this is neither odd nor even. This function down here has origin symmetry. If you rotate this graph 180 degrees, it will be the same graph. So it's not an even function, it's an odd function. This function here is symmetric about the y-axis. It's like the y-axis is a mirror that cuts it in half. So that function has y-axis symmetry. That function is an even function. And number 27, I'd like you to try that and see whether that's odd, even, or neither. As you can see, it does not have y-axis symmetry because it's not the same thing going on both sides, and it does not have origin symmetry because it's a corresponding point 3, 1 does not have a corresponding point -3, -1. So this guy is neither. And as you can see for number 28, it's similar situation. This one neither has y-axis nor origin symmetry. So you can tell relatively quickly from the graph whether it has y-axis symmetry or origin symmetry, and therefore whether the graph is an even function or an odd function. Now we're going to determine whether these functions are odd or even algebraically. So Let's see if we can do a few of these. I'll do some of them and I'll leave some of them for you to attempt on your own. So let's try number 35. To check for symmetry, to check for odd or even, we just replace x with negative x and see if you either get the original function or the negative of the original function. And as you can see here, this is the negative of f of x, which makes this an odd function. For number 34, I replace my x with negative x in every part of this expression, and that gave me the original expression that I started out with. So this gives me an even function. For number 35, again, I replace my x with negative x. And when I simplify this, I get the original equation, the original expression. And because that is, I know then that I'm dealing with an even function. For number 36, I replace my x with negative x, and I simplify. And when I do not get the same as the original expression. And when I factor out negative 1, what's in the parentheses is not the same as the original expression either. So we're saying it's not an even function, and it is not an odd function. So we're talking about a function that is neither. For number 37, well, let's skip that. We did one of that's similar earlier, so I'll leave you to do that one. Number 38, I replace my x with negative x, and I get square root of negative x. Now, I cannot factor out a negative out of a square root like I could with a cube root, as I could with number 37. With number 37, I could have taken out the negative because it's an odd index, but an even index, we could not do that. So as a result, we are stuck here. And so this is not the same as the original, and this is not the negative of the original. So we're talking about a graph that is neither odd nor even. Neither odd nor even. Now let's talk about this function here. We replace all my x's with negative x. So we get negative x plus the absolute value of negative x. And that just gives me negative x plus the absolute value of x. That is not the same as the original function. And that, of course, is not the same as the negative of the original function. So we're talking about it's neither odd nor even. And as you can see here, when you add this is an odd function, that's an even function. When you add them together, you get neither, as our shortcut would indicate. Let's try number 40. If I replace my x with negative x, I replace all my x's with negative x, and then I simplify. When I square negative x, I get the same as when I square a positive, so I get 2x squared plus 1 under a cube root, which is the same as what I had before. That is equal to the original function, so we're talking about an even function here, an even function. With this one, if you take the reciprocal of a positive number, it's still positive. And if you take the reciprocal of a negative number, it's still negative. This is an even function, and I took the reciprocal of that function, so I should still have an even function. Let's see if we're correct. I replaced x with negative x, and so I get 1 over the square of negative x, which is 1 over x squared, which is my original function. So this is an even function. Then when I do h of negative x for number 42, that's an odd function divided by an even function. It's like negative divided by a positive would be negative. So odd function divided by even function should give me an odd function. So I have negative x over the square of negative x minus 1, which is negative of x over x squared minus 1. That is the negative of the original. So we're talking about an odd function here. And let's do these last two, even though I told you that I'd leave it to do them on your own. I would recommend you try them before you check. We replace all our x's with negative x. And then we simplify. And you see here that we end up with positive x cubed over 3x squared minus 9, which is not the original equation. But if I multiply the top, if I factor out a negative, I get negative of negative x cubed over 3x squared minus 9. That makes this function an odd function. So let me see if I can fit it in the spaces here. And then finally, let's try for this last example here. I'm going to replace all my x's with negative x again. And the absolute value of negative x is just the same as the absolute value of x, which gives me the negative of 2x over absolute value of x, which is the negative of the original function. So therefore, we're dealing with an odd function. All right, so far we've dealt with symmetry and odd and even functions. What we're going to go to next is how do we tell whether the function is increasing and decreasing, which what we'll do is you do it from the graph. So the next step is increasing, decreasing, and constant functions. Now we will finish up by focusing on a few other details about graphs of functions, namely where they're increasing, decreasing, or constant, and also where they have a relative maximum or minimum, and also to calculate the average rate of change. These are basic, very simple concepts, and you can determine these simply from the graph for the most part. First of all, let's talk a little bit about whether a function is increasing or decreasing or constant. Let's talk about increasing first. When we look at a graph on the interval from -6 to -2, we see that the graph is going upward from left to right. We read from left to right in English at least. So when we're reading a graph, we go from left to right. Since the graph is going upward, we say that the graph is increasing on that interval. So as you follow the graph of the function from x equal -6 to x equal to -2, the function values are getting higher and higher. And so we say that the graph is increasing on that open interval from -6 to -2. Very simple. Now, as you can see, the graph is also increasing at another interval. Can you see where it is? right, from 4 to 6. So the graph is also increasing on the interval from 4 to 6. Now let's take a look at another part of the graph. Let's see, we take a look at where the function is decreasing. As you can see, the function starts decreasing at -2 and keeps doing that until you get to 4. So the function is decreasing on the open interval from -2 to 4. All right, because the graph is going downward from left to right. Let's take a look at another graph here. From -7 to -2, as you can see, the graph is increasing because it's going upward. Then if you notice, when you go from -2 to 2, the graph does not go upward or downward at all, so the graph is constant. That means the y value does not change. A constant is a value that does not change. So we say the function has a constant value from -2 to 2, from x equals -2 to y equals to 2. From x equal to -2 to x equals to 2. Then, if we look from 2 to 7, you can see that the graph is again decreasing because the graph is going downward from x equal 2 to x equal to 7. And that's how simple that is. Now let's talk a little bit more about something else about the graph, namely the highest point of the graph and the lowest point of the graph in a region. We call that a local maximum point if the graph is, if you go a little bit to the left or a little bit to the right, the graph gets lower. It's the highest point in that region. You can tell from the graph because it's kind of like a mountaintop. And of course, that's the highest value of x in that region, the highest value of y in the region, the highest y value in that region, sorry, f of x equal to the highest point there. In this case, the point occurs at -2, so the maximum occurs at -2 and the maximum value is 5. So the graph increases before that point and then decreases after that point. So we say that it's a local maximum value. Likewise, we can talk about a local minimum value, and the plural for the word maximum is maxima, and the plural for the word minimum is minima. So the graph is decreasing before that point and then increasing after that point. So that's a local minimum. It's the lowest point in that region. Very simple concept. So let's take a quick look at a few examples here. This question says simply, for each function graphed below, determine A, the intercepts, B, the domain and range, C, the intervals on which it is increasing and decreasing or constant, and then maximum and minimum values. So let's take a quick look at those functions that we have here. We're going to give all our intervals using interval notation. All right. So for our first graph, we see that the graph has a y-intercept at 0, 3, an x-intercept at -2, 0, and another x-intercept at 2, 0. So y-intercept, let me just write this as part A. Y-intercept is at 0, 3, and x-intercepts are at -2, 0, and at 2, 0. Then for part B, the domain. The domain are the x values in question. So in this case, the domain, the lowest x value is -4, and that's included, and the highest x value is +4, which is also included, so it's brackets. The range, the lowest y value, the lowest point it goes down to is 0. That's the lowest y value we get, which is included, and the highest it goes up to is 3. So the range is bracket 0 to 3. Now let's talk about where the graph is increasing and decreasing. The graph is increasing on the intervals beginning from -2, where the intervals are x values, from -2 up to 0, and then it picks up again from 2 and stops at 4. See, the graph starts at -2 and it's going upward until you get to 0. Then it picks up again at 2 and keeps going upward until you get to 4. The graph is decreasing. Graph is decreasing, starts decreasing at -4 and stops decreasing at -2, and then picks up again from -4 to -2, decreasing, and then picks up at 0 and stops at 2. The graph is never constant, so we'll leave it as that. Part D, absolute maximum values, absolute maximum minimum values. So absolute maximum, that means the overall highest point on the graph is 3, and that's the highest point on the graph, and that occurs at x equal to 0. And the absolute minimum value, that means the lowest point on the graph, is 0, and that's a y value, and that occurs 2 places, at x equal to -2 and at x equals to +2. And there you have it. Think you can do the other questions similar to that one. Number 22 is very similar to number 21, so I'll leave you to do that one on your own. Very similar concept. Now let's take a look at number 23. For number 23, as you can see here, the graph does not touch the x-axis, it only touches the y-axis. So there's only a y-intercept. So this is the y-intercept, occurs at 0, 1, and that function is actually a familiar function, which you will see later in the course. Is the graph, is an exponential graph. There's no x-intercept. So I'll just indicate that there's no x-intercept, but that's not necessary to write in this case. Now for the domain, as you can see, there's an arrow pointing to the left, an arrow pointing to the right, which tells us that the graph keeps going forever to the left and forever to the right. So the domain reading from left to right is from -infinity to +infinity. Now, of course, infinity only uses parentheses. The range, the lowest the graph gets is almost to 0. It doesn't actually get to 0, so there's a parenthesis at 0. And then the graph keeps going upward forever. So the range is an open interval from 0 to infinity. And as you can see here, the graph is increasing all the time. It's always increasing. It's never decreasing. So it's increasing for its whole domain, which is from -infinity to infinity. And then we're asking what's the maximum value and what's the minimum value. As you can see, the graph doesn't have a lowest point or a highest point. So there's no maximum value and no minimum value. And I'd like to point out that even though it doesn't go lower than 0, it actually doesn't get to 0, so it doesn't actually have a lowest point. It's kind of a weird situation with what we call open intervals, where you can get closer and closer to a number but never actually get there, so you don't actually have a lowest point. Last example in this page, we have this function here, which is the domain. The y-intercept is no y-intercept, so again, we don't need that, but the x-intercept is at 1, 0. The domain, as you can see, the graph does not go all the way to the left. It just keeps going closer and closer to the y-axis. So the lowest x value you can get is almost to 0, and it keeps going on forever to the right. The range, on the other hand, keeps going downward forever and upward forever. That means you're going from -infinity to infinity. And as you can see, the graph is always increasing on its domain again. But the domain is different from the previous graph. This domain is from 0 to positive infinity. And again, just as before, the graph has no maximum point and no minimum. No maximum, no minimum. All right, now this graph is also a special graph. That's a logarithmic function. Now let's try another set of examples here. In this case, same instructions. As we can tell from the graph here, the intercept, there's only one intercept, either x and y intercept in number 25. It crosses both the x and y axes at 0, 0. So the intercept, the one intercept is at the point 0, 0. That's not an interval, that's a point. Then the domain of the function is pretty clear from the graph again, that the lowest value is at negative pi, and the highest value is at positive pi. And then the range, the lowest value we get is lowest value is down to -1, and the highest value is up to +1. As you can see, this is an odd function. Now this graph is increasing. This graph is increasing in one spot, one place. It starts increasing from -pi/2 and stops decreasing at pi/2. That's an open interval. On the other hand, it's decreasing at the other intervals in this domain. So the graph starts decreasing at -pi and stops decreasing at -pi/2. And then it picks it up again from +pi/2 to pi. And then finally, the maximum value, the absolute maximum value here is at 1, and the absolute minimum value is -1. So absolute maximum is the value y equal 1, and that occurs at x equal to pi/2. And the absolute minimum value is -1, and that occurs at x equals to -pi/2. I leave you to do number 26 on your own while we look at number 27. For number 27, you can see that the graph has a y-intercept at 0, half, and the x-intercepts, not very easy to see. One of them is at 1/3, 0. The other one, as you can see, the slope of this graph is it goes from -1 to 1, so that's up to and goes over 1, so it crosses halfway there. So the x-intercept is at 2.5, which is 5/2, 0. The domain, again, we can tell very easily. The lowest value of the graph is it starts at -3, the lowest x value, and goes all the way up to +3. And then the range, the lowest y value we can have on the graph is -1, multiple points. Highest y value was at +2. It's the highest it went to. Part C, the graph is increasing on the interval from -2 to 3. Then the graph is decreasing decreasing from -1, that's a point right here, the x-coordinate, until +1. And then the graph is constant, and that means neither increasing nor decreasing on the following interval. Starts being constant at -3, then stops being constant at -1. Then it picks up that again at 1, and then stops at 2. So I see the x value here, -3 to -1, and then picks up at 1 and stops at 2. And then finally, maximum value is, as we indicated, 2, and it occurs when x is between the values of -3 and -1, and the minimum value is -1, and that occurs when x is between the values of 1 and 2. Now, as before, I'm going to leave you to try this next question here, number 28, on your own with the same idea. Let us move on to the last concept for this lesson, which is finding the average rate of change. And that concept is very simple. All we're doing is finding the rate of change from beginning to end of this interval. Basically, we're finding the slope of the line segment that goes from this starting point to this ending point. And basically, we're just finding the slope, as we said. So we just use the slope formula, m equal to y2 minus y1 over x2 minus x1, and do y2 8 minus y1 0 over x2 7 minus x1 0, and simplify, and that's our slope. Very simple procedure. So the average rate of change from this point to this point is 8 over 7 y units per x unit. Let's try these last two examples, and that will be the end of our lesson. Okay, so questions are from Algebra and Trigonometry by Sullivan, section 3.3. So we take a look at the first question, which says, find the average rate of change from 2 to 5 and find an equation for the secant line containing those 2 points. The secant line is a line segment, that goes through these 2 points on the graph, this point here to that point there. So basically, it's the slope of the line segment. Now, if you notice, this is already a straight line. So the average rate of change of a straight line is the slope of that line. So let's see if that confirms our idea. The average rate of change, so average rate of change is equal to f of 5 minus f of 2 divided by 5 minus 2. Now f of 5 is -4 times 5 plus 1. And f of 2 is -4 times 2 plus 1. So basically, I just plug in the x values. And of course, 5 minus 2 is 3. So when I work that out, -4 times 5 plus 1 is -19, minus -4 plus times 2 plus 1 is -7. And we're dividing by 3. -19 minus -7 is -12 divided by 3, and that is -4. Exactly the same as the slope that we had before, because it's a straight line. So since it's a straight line, the slope will be whatever the rate of change is. So that means the equation will be the same equation we have here. Let us check. To find the equation, we know that f of 2 is -7 and f of 5 is -19. And I can just choose a point and use my point slope formula. Y minus y1 is equal to m times x minus x1. And my m is the average rate of change. This guy here is my slope of the secant line. So I choose a point. Let's say we choose the point 2, -7. So that means my x coordinate will be, my x1 will be 2 and my y1 will be -7. So I do y minus -7 equals to the slope, which is -4 times x minus 2. And then I solve. So I get y plus 7 is equal to -4x plus 8 because I simply distribute the -4. And then I solve for y. I get y is equal to -4x plus 1. Again, what we expected because we were working with a straight line. So the average rate of change of a straight line is the slope of the straight line. And the equation of the secant of a straight line is this equation of the line because the line is its own secant line. Let's try something a little bit more challenging, which is this example here. Now, in this case, I need to find g of -1, which is -1 squared plus 1, which is 2, and g of 2, which is 2 squared plus 1, which is 5. And then, to find the average rate of change, I simply do g of 2 minus g of -1 divided by 2 minus -1. That gives me 5 minus 2 over 2 minus -1, 2 plus 1. We see that's 3 over 3, which is 1. So the average rate of change is 1. Now let's go to the equation of the secant line. Again, the equation of the secant line is found by doing all the things we would normally do with a straight line, but the slope in this case is the average rate of change. So we can choose the point, use the point -1 comma g of -1, so which is the same as using -1 comma 2. So I just plug in the values. Y minus 2 is equal to slope 1 x minus -1. So y minus 2 is equal to x plus 1. So y is equal to x plus 3. And that is the end of that question. That's the equation of the secant line. So the average rate of change is just the slope of the line segment joining the endpoints. And that is all for the lesson for today. As always, I recommend strongly, very strongly, that you check out Khan Academy because they have some excellent videos and exercises for you to practice these questions. And I also recommend that you practice these questions from your textbook, your course textbook, as well as from the other textbooks that are recommended on such apps and sites as openstax.org, openstax.org. And that is all for today. That's our lesson. Have a wonderful time and make sure you keep practicing that math.